very much. We'll move to the. It's a great, lot of questions on map projections. Clearly, it's a very important topic. Um, we are running a little behind, so I'll keep my presentation as short as possible. Um, uh, can we? I guess they control it. So it's a last presentation. So as they do it, I want to acknowledge that I met Lynn many years ago, probably 12 years ago, and I started working with him on ontology. So he was passionate about ontology and mapping, and so I worked on GeoVocamps with him, and I got to know him through that. And then Sam came along, and then Sam and I worked together. So this work is very much in honor of Lynn, and it'll continue with a lot of people at CGIS. Genevieve is my student. Weil was my student. They worked on this with me. I had this idea of continuing something from a dissertation from 15 years ago. I never found students who would do that. So a lot of this work I feel is almost like historical GIS work. It's something should have happened 15 years ago, but it's happening now. Thanks to my students. Genevieve couldn't come. She should have presented this, so I'm doing it on her behalf here. So I'll begin with an example that again comes from Lynn actually. So when we used to work on vocamps, his problem was, as you know, most of you know that GNIS, Geography Names Information System, has only points. And Sam alluded to that we need, to work on named landforms, people care about them, and all we have is points for them. So Lynn used to talk about the Grand Canyon a lot. I'll skip to that slide. If you search for Grand Canyon on the USGS national map, you get this, right? Grand Canyon is this point. All right? This is what is pervading everywhere, right? And Lynn's point was, I want to describe land, I want to search, I want to search fire, this is if there's a fire or somebody's lost and we want to search, describe position. And all you can say is, I don't even know if I'm in the Grand Canyon, it's so big, but I don't know when I'm in it or not, right? And of course on mountain slopes and which slope and which facing. So that's, and I was passionate about it. My advisor, David Mark, who passed away, was passionate about it. And so we got together and started working on this. It's been a long time. We haven't really achieved what we should have by now, but hopefully we will. And so if you see, this is also on Wikipedia. Like Wikipedia, very proudly lists a point for a Grand Canyon. All right, and this is the problem we have right now. So we want essentially aerial extents. Very simple task is, could we have some aerial footprint for these landforms, right? That would allow us to, doesn't have to be one, a process maybe that can be adjusted, but let's get towards aerial representations rather than the points, which is what Sam and I are trying to work on, right? And maybe it can be solved, I don't know, but I think Lynn believed it could be, so we'll continue. I didn't used to think a whole lot about extracting features, landforms. I did that, 15 years ago, and I kind of walked away from it because I couldn't find partners who would want to work with me on that. And eventually I found CGIS, and since then I've really cherished this work and I want to continue doing this. It's not just for genus aerial extents. I think if you start thinking about landforms, think of it as like in the spirit of this conference, have some empathy for landforms, they are actually, people treat them as objects in indigenous cultures. They are actually very important. They are sacred places in a lot of cases, right? So it's not just in cartography, okay, it's a label. In GIS, it's an elevation surface from which, if you want, you can extract out something. But for people, they actually matter. There are a lot of cases where you actually can personify landforms. So I think there's a lot of value in treating landforms as sort of cultural beings, right? They live in our text, they live in maps, they live in our mental maps, they live in our experiences. We hike and do things. So how do I bring all of that together, a very multimodal idea of landforms into the next generation GIS? That's what at least I'm inspired by. So the most obviously tangible task right now is to give them a 2D footprint, right? But let's not just forget where we can go with that in the next 20, 30 years, all right? So that's what I wanted to talk about. Most important, the rest of it is just pedantic details, which I can bore you with. So general geomorphometry, is a basic idea. Most of us know of slope aspect. That's what we get from elevation surfaces, and that's a continuous description of terrain. So the idea of general geomorphometry is where you take the elevation surface as a beginning point, and then you classify it, segment it. But the focus is not on extracting individual objects that you could measure or worry about or name them or make them your own. There's like segments of the continuous landscape. Trying to describe the land as a sort of a discrete set of elements, but these elements don't have real identity per se. All right. So here is a screenshot from a paper published in 2017. They compared a bunch of methods for soil mapping, right? And this was the inspiration for me to find work for a student of mine, Hassan, who wasn't good at programming, but he wanted to work with me on topography mapping. So I said, why don't you work with this? And instead of these people were doing it for soil mapping. They wanted to compare how soil experts classified landforms at different places. I want to do it for more macro level cultural recognition landforms. I knew these methods don't quite work. I've already tried this informally, but I've never, to say that something doesn't work requires a lot more work and effort, and I've never had the time. So I said, you know what, this is the perfect thing for you. Help me show that this doesn't work, because ethically I can't say that it doesn't work just because I think my method is better. So I wanted to prove this, all right? So that's where we are going. What you're seeing here is just how different kinds of landform elements will show up based on a few methods. So what we did was we picked up 3 Woods morphometric features. There's topographic position index and a geomorphon. These methods is what we picked for thesis work. And then in parallel, I forgot this slide was coming up. Sam and I looked at Geobia, which is a pretty hot method, right? And Geobia ended up, we published this in the Cages journal. And Geobia doesn't give you very reliable one-to-one mapping for named landforms as well. So you can get polygons, but then they don't quite match up with what people would draw as possible extents of landforms. The Geobia, again, I would say it's a general geomorphometry method. It's not a specific geomorphometry method, which I conclude with. So here is an example of what a topographic position index, a very simple method. You can change the scale. At small scales, you will get features. You can see that in the top diagram there. The same location is a lower slope or a ridge, but if you expand the scale of your analysis, you can see that the ridge is actually sitting at the bottom of a valley, right? So scale obviously is something we understand intuitively, and that affects what you classify a certain position as, right? It's a position and the analysis. So both are okay, it just depends on what you want to do, right? It's a very simple method. So we did this. This is the benthic terrain model, very similar method, but it was for bathymetric features, but the idea is very similar. You can adapt it, and so we did. Genevieve is right now using this to figure out what happens when you use this to classify landforms and see if they correlate with what we would name or not. This is Wood's method. I'm just rushing through this for lack of time, but this is a very simple method. You look around, if it's a peak or a pit or a flat pass, channel. These are the 6 classes, and the map shows you what it looks like. Now, I have known about this method for 25 years. He's published and he's shown that it works very well. I've never found it to work very well for my use case. So I've always had trouble with this. So I didn't use this, but so we evaluate. And then this is the latest method, 2012, very, very smart method called geomorphons based on not local differential geometry, but visibility. So look around and see how far you can see, and that from the visibility, they infer a few shapes that allow you to create local landform shapes, right? Now, the problem is, will this scale up to more macro level landforms? Can you detect a mountain from piecing together some of these? And can we just change window size? So all of these come with parameters, right? You have scale, which is essentially the window of your analysis, the window size, moving window analysis, and then slope or curvature. So what we devised was a just very simple run through a whole bunch of experiments. Right, choose all these parameters. So I'm only reporting on the 2 that are very popular, partly because Weil started this, and these methods are easily available in GrassGIS. You can call it through Quantum GIS. He didn't know how to program. He didn't know how to Python code. I said, pick these, and these are the 2 most popular ones everybody uses. And I know that they claim that it can do a lot of morphometric mapping. So let's see what happens. So we changed, we set a few parameters, in window size, outer window, inner search radius, whatever, slope thresholds, curvature. And so we did 60 runs, 80 runs for these based on the parameters. And then he visually looked through it. The problem is there's no one quantification method that you can use, right? So let me just show you a few results. And we did it for 3 study areas. White Mountains, very glaciated, very similar Smoky Mountains. And then we picked Colorado Plateau. I've used this in my dissertation. This is an area where almost every method I come up with and the like fails. So I pick this always, and this always keeps you from over assessing, your method, right? So this is a diagram. It's a panel, right, based on different slope thresholds. This is for Wood's morphometric features. What we found is that a certain range of threshold, 0.001, 0.001, curvature, slope, it's a little painful. I've never understood, because you have to keep playing around and get results through these methods, and I don't quite know intuitively what to pick. So he narrowed it down to a window size of 30 to 40 for a 10 meter, so it's 300 meters to 400 meters. You start getting some peaks, so you can see the color here. We were focused mostly on summits and ridges. In this case, it should be peak, it's wrongly labeled. But it's still, I mean, the best still doesn't impress me. I don't know how Wood got results that he got. I haven't been able to replicate it. All right. So Genevieve came in and she wanted to do a bit more a quantitative assessment. So she actually did an R analysis, and she plotted the amount of peaks we got, or I don't know if it's the area of the peaks of the cells, whichever way it's correlated. What happens with window size, slope, curvature? These are the thresholds for that method. And as you can see, for ridges, there is sort of a clear pattern for all. For peaks, window size, slope, curvature, I mean, window size doesn't seem to matter, which was counterintuitive to me. Slope, as you can see, as the slope increases, the size of the peaks increases, and it becomes very crazy. And these results are not exactly the same for my other Colorado Plateau area. It gives us slightly different results. I haven't quite understood fully what this means, but all I can tell is that I don't like this method. And if you see this is just showing you what happens when you change the curvature, slope, and all. The area of these things keep increasing. If you just focus on mapping mountaintops, none of them look very attractive to me. Sometimes it works, sometimes it doesn't. Sometimes it appears on the side of the slope. So it's beginning to confirm what I've suspected for 15 years, that this will not work, and the USGS needs something scalable across the nation for different terrain types. It's not going to work, I think. So anyways, this is a summary of this, 5-degree slope, 5 to 10 for depending on what you want to map, curvature slides. We need to do more. Similarly, the same thing comes up with geomorphon. I think the results for geomorphon is a newer method are better, much better. So this is what I recommend if you want to use an off-the-shelf method, try to use this, all right? Here you can see that the study area doesn't affect. So all 3 study areas came up with very similar results in terms of how they impact the number of peaks or the size of the peaks. This doesn't look very good, but I think when we try to quantify things and look at them, there is quite a variation in what that mountaintop looks like depending on which parameter you choose, which again gives me a little bit of pause as to what do I know is good. The problem is I don't know what is good or what works, and for that we'll have to talk to people and do testing. Then what we did was finally, we compared these, just for the mountaintops that we got, summit areas supposedly, from these methods, we compared with genus points that people have already known and mapped. And what we're finding is that if you want to look at a mountaintop that looks like something that people might agree that that's the rough area, if you map with contours and passes, they don't give very good results as to where the genus point is. The genus point is somewhere else, or it doesn't match up. There's when we try to minimize the distance between the nearest genus point and the summit point, we find that the parameters we thought were very good based on visual analysis, they don't match up. So there's a huge disconnect between, if I'm trying to find a polygon to represent that named peak, the parameters that I have to choose, when I look at what it looks like on the map, it looks horrible. And so it's just not working. So we don't have a solution yet. And so it's more negative results. And then we compared the confusion matrix analysis of methods. So the best model from the Wood, best model from geomorphon, when we did a cross method, looks like that the peak from one method and the summit from this method, they seem to have some semantic similarity, but not always. So there's the whole ontology semantics aspect of this. Just because somebody calls it a summit or a peak doesn't mean that it's the same thing in every method. It comes up as different things, and there are nuances that we have to be teased out. All right. So that's roughly the end of my presentation. I have 1 minute left. So what I want to show you is this general approach of taking a pixel, or GeoBI, a series of pixels, and trying to extract out individualized extents of what people might recognize as meaningful landform objects is unlikely to work. Now, There is a lot of work going on deep learning and machine learning and artificial intelligence. Sam is an expert on that. She's working. I just got a request to review a paper today, by the way, Sam, on deep learning application. But I think that's, again, a continuous general geomorphometry approach. So Sam and I are also working on, I'm going to skip this ontology stuff. It doesn't matter to this presentation. We worked on a paper and we published this in a geomorphometry conference paper. This is a very simple old method that I worked on my dissertation 15 years ago. We're going back to basics. Pick a peak and do a simple region, one by one. You find peaks and you start growing a region around them based on, and this, you can see Sam also has access to landforms delineated by actual USGS staff for a slightly different purpose. So in this map, what you're seeing is manually delineated polygons are in red, and a simple method that I've used in blue. What happens is the blue ones seem to be larger often. They don't quite capture what people may have captured, but you must remember they were using topographic labels to decide what is the extent of a landform. All right, we weren't quite doing that. We were doing it based on sort of shape. But this one guarantees that there is a polygon, exactly one polygon for that. And I haven't yet found, after 15 years, a method that does any better. There are other similar methods. I think the answer lies in the specific geomorphometry realm, not in the general geomorphometry. So all those off-the-shelf, very easy to use software will not get us anywhere that the USGS needs to. And so that's what I think I'm going to write up for the special issue. Thank you.